All right, let's start. Does it work? Okay, perfect. So the original plan was to start discussing gauge theory today, but then I changed my mind, and we have one more topic before we start gauge theory, and that's some glimpse into topology of the space of solutions of the EL equations. So let me recall that up to now the situation was as follows. So we had the space of fields was the space of maps from the space-time to a vector space. So as such, this was a vector space. And also in the case of M being R times sigma, we identified, or we hope to identify solely L with F sigma, which was the space of values of fields on sigma together with their time derivatives. And you can also think that these are maps from sigma to V plus V. And this is also a vector space. So up to now, there is not that much topology in this theory. So let me start with an example that we know very well, and let me introduce more topological considerations there. Let's consider a scalar field on R times a circle. So V is R. As usual, L is 1/2 d naught phi squared minus d1 phi squared dx naught dx1. And EL equation is the wave equation. So d naught phi squared, d naught squared phi minus d1 squared phi equal to 0. Now let me recall that we already once discussed solutions of the wave equation in dimension 1. So solve EL looks like this. Phi of x naught x1 is a function of x naught minus x1 plus a function of x naught plus x1. So let's perhaps discuss it in a little bit more detail. Now, so phi is a function from R times a circle to the real line. Well, what about f and g? So let's think of f and g as functions from R to R, but then we need some kind of periodicity conditions on them because we want the resulting function to be a function on R times S1. So in fact, we need them to be quasi-periodic, meaning the following. F of S plus 2 pi is f of s possibly plus something, and then g of s plus 2 pi will be g of s. If I'm not mistaken, how is it? Plus the same thing, right? So here the periodicity should be in the coordinate x1. So if we add something, it's say if we subtract 2 pi, or if we add 2 pi to x1, then f of f will change by minus c. At the same time, we add 2 pi here to this argument, so g is increased by c, so all in all we get a periodic function. Right? So phi x0, x1 is periodic in x1. Okay, so that's something that we know very well. Now let's say we replace v, which is the real line. Let's replace it by v, which is also going to be S1. So what does it mean in practice? So S1, we can say, is R over 2 pi z. So so this expression in some way still makes sense. Let me just think that my v, if you want to think of it as still real valued, but we identify our real values which are different by 2 pi z. So this expression still makes sense. The only thing which changes is the space of solutions. In principle now, we don't need phi to be periodic in x1. It can also be quasi-periodic. So when you go around, it can change by 2 pi n. So this means that in principle here, I can add 2 pi n. Right? So this will be, now f is quasi-periodic, g is quasi-periodic, and now phi is also quasi-periodic with a shift which is divisible by 2 pi. Right. So let's spell it in a slightly different way. So now let's say our phi, if we fix x0 and we view it as a function of x1. Now this is a map from S1 to S1. Homotopy classes of such maps are classified by the fundamental group by definition. So the fundamental group of S1 is, of course, Z. Now, so we have such a map. To such a map, how can we, like that's the standard things, the first things you learn when you learn about the fundamental group. How can you think about it? To such a map, you can assign the degree. And the degree of phi, what is it? Like, let me write two expressions for it, and you confirm that you agree or disagree. So either you can say that's the number of preimages, so phi minus 1 of some value, let's say theta, for a generic fiber. And you take this, maybe better say, sum minus 1 to the epsilon p phi of p is equal to is equal to theta, right? So you consider pre-images of a given point. Now you have an orientation. Your circles are oriented. So at a given point, the differential of the map either preserves orientation or reverses the orientation. You take the sum of those plus or minus ones over all pre-images, and you get an integer, which is the degree. Or I can now write it in a different way. I can probably just write it as 1 over 2 pi integral 0 to 2 pi d1 phi dx1. Just an integral of the derivative d1 phi of my map. So actually, if we go back to the space of solutions, so this will be exactly this n, right? This will be this integer n that I introduced in the space of solutions. So let me recall that when we were discussing Noether currents, in a similar situation, we had the following expression, right? I think it was a minus for some reason, integral of the time derivative of phi dx1. And this was a conserved Noether charge, right? So this thing was conserved because there was some symmetry in this theory. The physicist would call the degree of this map a topological charge, in analogy to the Noether charge. Of course, this expression cannot change with time, just because it's a homotopy invariant, right? Of course, the expressions, they do look somewhat similar, right? It's an integral of one of the derivatives. Now here it's an integral of a time derivative, and here it's an integral of the space derivative. Perhaps one more thing. So we have our Sol EL. We have this Noether charge Q, which maps it to R. And we have this topological charge, or whatever, degree phi, which maps it to Z. And, well, I think I have one more corner. So this tells us that Sol L is a disjoint union of spaces Sol EL n, which are phis in Sol EL with a degree of phi equal to n. Right, so here all of a sudden we changed the topology. Once we changed the topology of the target, now the space Sol L becomes topologically more interesting. So things may happen now. It's not necessarily just a vector space. And, well, so that's, of course, a very, very simple elementary observation that S1 maps from S1 to S1 have a degree. So degree is an integer. And here we kind of observe this degree in this very, very simple framework. Now, perhaps what I want to do, I want to put this story in a somewhat more regular context. So let's discuss what happens if we replace V as a vector space by V, which is a manifold. So how does it, how the corresponding Lagrangians look like? And this goes under the name of nonlinear sigma models. So what we were doing before, these were, so to say, linear sigma models. If I'm not mistaken, sigma just comes from the fact that at some point the map from the space-time to a manifold was called sigma by someone. Since then, it's called sigma, even though we call it phi. So strictly speaking, we study nonlinear phi models. But okay, so M is a manifold, and now V is also a manifold. And the space of fields is a space of maps, some kind of maps from M to V. So for phi in F and M in M, as usual, phi of M is now a point of V. And perhaps what would be interesting for us is the differential of phi at the point M. So, well, as usual, that's a map from the tangent space to the tangent space. Or perhaps let me write it in the following way. So that's just saying the same. So this is an element of the vector space of Homs from one vector space to the other. Now, in general, if I want to write a Lagrangian which depends on phi and its derivatives, so this will be L of phi and d phi. So phi would be an element of V now. D phi is just a linear map, so an element of in this vector space D and X. So that's this guy is in V. So this guy is in Hom. Now it does not make that much sense to ask that the dependence on phi to be polynomial, because we don't know what that means. So it's just a function on V. Here we can still require the dependence to be polynomial, which sounds reasonable. Now d and x should be, again, top degree, beta perhaps non-vanishing, so volume form on M. Let me give a concrete example of how this may. So I'll give several mechanisms, several constructions, how you typically build those Lagrangians. One example is as follows. So suppose we have H a Riemannian metric, or maybe pseudo-Riemannian, but let's say Riemannian to start with, Riemannian metric on M. So HM, if we think of a point M of M, so what is it? So that's a map from TMM tensor squared to R. Right? So we can think of it as being an element of Tm star m tensor squared, right? So that's a possibility to think of a Riemannian metric in this way. So it's non-degenerate. So therefore, we can introduce its inverse as a map from Tm star m tensor squared to R, right? So we have here canonical element. We can take the dual canonical element in the dual vector space. Or we can think of it as an element of Tm tensor squared. That's similar to the relation that we discussed between the Poisson bivector and symplectic form. They were skew-symmetric. One was the inverse of the other. Here, in a similar fashion, I now I transport my metric to the cotangent space. The other way to think about it, the metric gives you an isomorphism between the tangent space and the cotangent space. Then just transport your metric from the tangent space to the cotangent space. So that's this guy. So that's one piece of data. So the other piece of data that I need is G the Riemannian metric on V. So GV maps the tangent space to V to R, or again, we can think of it as a dual tensor squared. We can also, of course, introduce the inverse, but we won't need it. So let me write L of phi d phi. So I'll write a formula, and then we'll try to understand why it makes sense. So it will be a pairing between hm minus 1 tensor G phi of m, and here d phi tensor d phi. Usually one puts 1/2. So let's see what's the nature of the quantities which participate. So this guy is in tensor square of Tmm. So this guy is in T phi of m star V tensor T phi of m star V. Right, so that's the nature of this tensor product. Now, what's the nature of this guy? Right, this is home Tm T phi of mv, so I can dualize this one, right? So here I have T star mm tensor T phi of mv times T star mm T phi of mv. Right, so that's the nature of the quantities. Now observe that, of course, everything is arranged nicely such that there is a perfect duality between the objects, right? And on top of it, here it's symmetric, here it's symmetric, here it's symmetric, so it doesn't really matter how you pair. Right. So there is a canonical pairing, and this gives you a function on M once you implement everything. So usually the notation, sometimes you can see the notation like that. But that's just a notation for this kind of writing. So given these two metrics, we can write such a Lagrangian function. And recall that since we have a Riemannian metric on M, we also have a canonically Riemannian volume element. Right? On M. So now we can use this expression L of phi d phi as above and multiply it by this Riemannian volume element. And this will be element in omega and 0 on M cross F. And that's a good starting point for Lagrangian field theory, as we were discussing it before. In fact, in the problem set, there will be an exercise. Right, we started today's lecture with the story of a scalar field with values in S1. Now, we had this little bit of a horror story, right? This complicated story with nonlinear sigma models. Now, the exercise is as follows. Suppose that you take M to be R cross S1, and we take H to be dx naught squared plus dx1 squared, the normal metric on this space. So now we take V to be also S1. And we take G to be d theta squared. Just that's the natural, theta is a natural coordinate on S1, just take this metric. Right? Now, so suppose you load this data into this expression. So the question is, what do you get? Do you get the expression I started with? What would be your first reaction? Hopefully, yes. Or maybe not quite, right? Maybe I wanted the Minkowski. Here let's say. But if I put a minus sign here, normally I should get the expression I started with. So in the problem set, the question will be what happens if you change something here. For instance, if you multiply by some number. So you want the circle of some radius. So then how it's gonna, what it's gonna do to the action. So first of all, reproduce, so reproduce the action or the Lagrangian density we had before, and then figure out what happens if the size of the circle changes. Right. Okay. So this was one example of how we can write Lagrangian densities. But actually, there are other ways as well. So let me show you two of them. So let's back to topology. So let's introduce so-called topological terms. So let me again start with an example. So let me choose M to be a two-sphere, S2. And let me choose V to be also a two-sphere. So phi will be an element in the space of maps from M to V. And well, again, this map has a degree. So this is, again, you can write two formulas. Either this is a sum of pre-images in a typical fiber with a sign which corresponds to the orientation. Typical fiber. Or we can do the following, right? I want to write a similar integral formula. So what would be a good integral formula? Would you have a suggestion? Right, before, remember, this was an integral of d1 phi. Now, so I have a map from this two-sphere to two-sphere, so I would like to compute the degree with an integral formula. Right, obviously, this should be some integral over S2, but of what? So let me make a suggestion, and then we'll see how it works. So I would take phi star of omega, where omega will be a two-form on the sphere. Now this will be a two-form which is identified as the target. So I have a form on the target sphere, which is the volume form. And I would normalize this volume form to have volume 1. In fact, recall that what we were doing with the scalar field, we took S1, and on S1 we can take the volume form 1 over 2 pi d theta. So this volume form is normalized such that the integral is equal to 1. And our topological charge, integral over 2 pi d1 phi dx1, 1 over 2 pi, is actually equal to the integral of the pullback of 1 over 2 pi d theta, right? So that's actually the same system. So would you agree on such a Does it sound okay? Maybe like try to refresh your memory why it actually works. Perhaps just to just to give a concrete example, right? I said choose a volume form, but we can give a concrete example. So if you go back to our symplectic geometry course, there we did have such a volume form on the sphere, just an invariant volume form. And maybe as a small exercise, I can give you the following. So suppose that I embed S2 in R3, and now I denote an element of S2 by n, and so now it's a 3 vector, right? So then, if I'm not mistaken, the standard symplectic form on the sphere can be written in the following form. So now I'm using just vector notations. This is a cross product or vector product in R3. I take the differentials of n. I take the cross product, and then I take the standard R3 Euclidean scalar product with n. Right? This gives me a 2 form on the sphere embedded in R3.
Sorry, the product of the vector with itself is 0.
Usually yes,
Okay.
but not now.
Okay.
Why? They're forms, right? So the product is skew-symmetric. That's like a Lie bracket. So this is secretly a Lie bracket, right? So the cross product is skew-symmetric, but the wedge product is also skew-symmetric. Probably if I want to write it more precisely, I should also put some wedge somewhere in between. So that's a wedge of forms and a cross product of vectors, but the notation is too ugly. So I mean, we understand that there is a cross product, there is a wedge product somewhere. So this is an example of such a form. Now, maybe to go back here. So what's going on here? We have M cross F, which is as usual maps from M to V. So there is the evaluation map to V, and there is a projection pi to F. There is, of course, another projection P to M, but that's something that we're rarely using. And in general, what we can do is suppose that there is a form on V. We can try to do the following. We take the pullback of omega under the evaluation map, so it maps here. And then after that, we can take a fiber integral. Right? So if this was a form of degree, say, k, the fiber integral takes away degree n. So this will be a form of degree k minus n on V. So ideally, at least in our context, we choose k equal to n to obtain a function on F. So note that I started with m equal to S2. So therefore, if I run this construction, this will give me the value of the degree of such a map. But what I can do, I can also take M to be some domain of R2. I can still very well run this construction. So this will give me some kind of function, let me call it S top of phi, which is just given by this expression. In other words, by the integral over m phi star of omega. Usually what happens, typically people don't study the variational problem or variational calculus for this functional. Instead, one takes the functional defined by the sigma model, and one usually adds a functional of this type. So that's so in physics, a typical problem would be for the functional s of phi, which is equal to s sigma model of phi, which depends on, say, two metrics, the metric on the space-time and the metric on the target. So the integral of this horror story plus the topological, so-called topological term, whatever that means. Of course, it refers to the fact that if you take a closed manifold, then you usually get some kind of degree. So this is a topological term plus S top omega of phi. And of course, so if M has no boundary, as we had in the case of S2, then typically what will happen, you will have Sol EL. And on Sol EL, you will have, so typically you arrange such that this guy then would take values in the integers. And similar to the situation before, we'll have a disjoint union of elements of Sol EL which correspond to different values of this number. But if the manifold is not, has a boundary, then in this case it becomes more interesting. So this kind of situation gives you some kind of interesting contributions. All right, so let's have a break. And after the break, I will tell you one more way of introducing topological terms, a kind of somewhat more complicated and more interesting way. And also I explain how the topology of Sol EL emerges from the dynamics of the Euler-Lagrange equations. So that's what happens after the break. All right, so let's continue. So I would like to show you one more kind of interesting way how to build functionals on the space of fields. So this is called Wess-Zumino terms. So again, so this is a functional that you typically add to some kind of nonlinear sigma model. But it's also kind of topologically interesting construction. So let's say we have M, a space-time of dimension n. Let's assume, to simplify things, that it has no boundary. So we take the target space V, and we consider the form of degree n plus 1 on V, which is closed. For instance, we can say that if the dimension of V is n plus 1 and eta is a volume form on V. So notice here there is a little bit of a difference in the numerology. So here we wanted a form of the same degree as the dimension of space-time. But now, interestingly, we want a form of degree 1 higher. Now let's assume that phi is a field. And let's assume that the image of M is homotopically trivial inside V, so it can be contracted to a point. So 0 trivial. So 5M contracted to a point. So we have, so this is our M. So this is our V. Phi maps to M, so that's the image phi of M, and this phi of M can be contracted to a point. In other words, maybe we can do the following. Let's introduce M hat to be a cone over M. So M divided by 0 times M corresponding to a point. So M hat is something like this. And we say that you can lift map phi to lift phi hat from M hat to V such that phi hat of 1M is equal to 5M. Right? So that's exactly means this picture. So here is this cone, and the map phi hat maps it to the contraction of M to a point. So let's define a functional WZ for Wess-Zumino of phi hat, and that would do exactly as I did before. Right now, we can say that M hat is of dimension n plus 1. So let's pull back the form eta using the map phi hat. And well, this will give us a number. So that's exactly the construction that we used before. Now, there is a small problem with it. It depends on phi hat and not on phi, right? So let's study this, the dependence on phi hat. Suppose we have two maps, phi hat and phi hat prime, which both map M to V and which both restrict to phi. So then in principle what we can do, we can glue these two maps into a map from, so here is M, here was one of those cones, here is another of those cones. So this is phi hat, this is phi hat prime. So we can glue it into a map from such a double cone into V. So let me denote this double cone by M tilde. So now Wess-Zumino phi minus Wess-Zumino of phi prime will be equal to, so let me denote this phi hat union phi hat prime as a phi tilde map. So this is an integral over M tilde phi tilde star of eta. Now M tilde, in contrast to M hat, has no boundary. So this is an integral of our closed form over some cycle inside V, one can say. So this is the same as phi tilde of M tilde eta. And this means that it belongs to the set of periods of eta, meaning exactly integrals of the form eta over the cycles inside V. So this is, so these are, by definition, these are integrals of eta over cycles in V. So this is a subgroup of R, so those periods. Now the question is, what kind of subgroup? Here perhaps I should add, so I should add a condition on, this is not that absolutely necessary, but typically that's convenient. So let's assume that I chose here eta in such a way that the periods are contained in Z. So assume eta is integral, that is periods of eta is contained in Z. So here we say it's contained in Z. We see that WZ of phi hat still does not quite descend to the boundary maps phi, to the maps from which we started. So in principle, if you extend in different ways, you still get different numbers, but these numbers are different by integers. Now, what one can do. And here we are already getting a glimpse of the quantum theory. So this implies that the map, exponential of 2 pi I WZ, from the space of fields to S1 is now well defined. Because now it is actually independent of the choice of the lift. So you chose different lifts, but this expression remains the same. Perhaps one more corollary of it. So we were thinking of variational calculus or differential calculus on the space of fields. So WZ is not well defined in general because there is this ambiguity. But the differential on the space of fields of WZ is also well defined. That's because under this assumption, the ambiguity is integer valued. Differentials of integers are 0. And this perhaps you can compare to the following observation. Suppose you consider a coordinate on the circle. So you have S1 and you have a coordinate theta. Theta is not a well-defined function on S1, unless, or you can make it well-defined, but then it's not continuous, it would jump. At 0 and at 2 pi. But this theta, the differential of this function, is a well-defined one form on S1. So that's similar here. So delta WZ is a well-defined one form.
So how do you define WZ if phi is not homotopically trivial? Is this defined for any field, any map?
No.
Right. So this exponential.
No, the definition I gave was only for
homotopically trivial map.
Right.
Okay, good.
Okay, in principle, yeah, maybe I can give a remark. Suppose that it's not homotopically trivial. Then what you can still do, you can do the following. So suppose that the homotopy class of phi in the space of maps from M to V is non-trivial, right? So then choose some standard map in this class. Now, of course, you will be able to build a cylinder between phi naught and phi. So phi hat will be a map from zero, 1 times M to V, which restricts to phi naught at one boundary, to phi at the other boundary. But then define the Wess-Zumino term which depends on the two boundary values. Now notice that this guy is still nicely defined. Of course, this expression will depend on your base map, but the differential does not depend on the base map, and this well defined. So if you're interested in classical theory, as we are now, so this would still give you some nicely defined functional that you can add to your action. And that's actually what happens in practice. That's why I'm talking to you about those constructions. So let me give you a concrete example. So M is equal to S2 and V is equal to S3, or if you want, we can identify it with a Lie group SU2. So now in this case, pi 2 of S3 is equal to 0. So therefore, phi always belongs to map 0 S2 to S3 because it coincides with all the space of maps. Now, eta, we can choose volume form on S3. Recall, if you think of S3 as SU2, recall that there is this interesting volume form that we were discussing a little bit last term. So this trace dgg minus 1 cube, written like in matrix notations. And so this produces for us, these are the data which are suitable for defining a Wess-Zumino term. So this gives us, so defines Wess-Zumino phi. Perhaps I should mention at the moment, perhaps it's not so interesting, but like there is a very famous example which is called in literature it's called WZW or WZNW of phi, and this is the sigma model action where you take a round metric on one sphere, a round metric on the other sphere. So H, G, the most standard metrics on S2 and S3. Plus you add Wess-Zumino of phi. And in principle, here you kind of, it depends on the normalization of this form. You can either say you kind of can change a coefficient here, or you can say that whatever, you can add some coefficient C here. And so maybe I should say about the names. So Wess and Zumino invented this method of creating topological terms, and this W is Witten, who figured out that this model becomes particularly interesting for one value of the coefficient C. So in general, that's a relatively complicated and obscure model. But for one particular value of the coefficient, it becomes a kind of wonderful model. And I think, literally speaking, there are probably like thousands of research papers written about this particular expression. I think thousands, that's not exaggeration. Who knows, maybe tens of thousands. I don't know. Like, right. So the literature about this expression is absolutely enormous. Now, so the letter N is for Novikov, and Novikov he was interested in the Morse theory, and in particular in the finite and infinite dimensional Morse theory, and he started thinking of Morse functions which are not necessarily univalued. So the functions which may be multivalued as our function here. So, and as the Wess-Zumino term is not strictly speaking well defined, right? I wrote the expression, but it does not quite make sense. So it makes sense mod z. So that's why sometimes one more letter is added. Right. So I would like to spend the last 20-25 minutes talking to you about another manifestation of topology in field theory. So now this was interesting, but somewhat simple-minded what we were doing. We had the space-time which was mapped to the target space, and we simply said, right, so there might be some topology of the space of maps, right? There might be homotopy classes of maps, and then, well, it would certainly influence the solutions of the early Lagrange equations. Now let me show you another example. Let me call it dynamical topological effects. So let me choose M to be R2, or maybe R1 plus 1. One of them is time, another one is space. So V will be R. So we are back to our friend, the scalar field. But now let me do the following. Let me say L is equal to 1/2 d0 phi squared minus 1/2 d1 phi squared minus some polynomial of phi, dx0, dx1. Now v of phi is called the potential. So the simplest example of a potential is just a quadratic polynomial proportional to phi square. So in the physics lingo, it's called the mass term. Notice that if you add the mass term, your theory remains what we call Gaussian or free, because it's so this polynomial remains quadratic in its variables. However, today we'll be interested in some other polynomial. Let me perhaps write it like this. So this is a quartic polynomial. Here there is some constant. Physicists would perhaps call it a coupling constant. For us, it's just a parameter. And the shape, the graph of this polynomial is like this. So it has minima at A and minus A. So let me write the EL equations. So the EL equations, so before we added the potential, this was a wave equation. Now what will happen, I hope I haven't mixed up the sign. So I think now there will be this term. By now you are great specialists in the EL equations. You can probably check it much better than I. So there will be there will be this term. Let me also write the energy. So the charge which corresponds to time translations. Again, you were supposed to get the general formula for it by whatever, 11:15, which is soon. Was it one of the problems? So let me write the expression. So E of phi d naught phi. I think, if I'm not mistaken, this should be this. 1/2 d naught phi square plus 1/2 d1 phi square plus what? Lambda over 4 phi square minus a square dx1, hopefully. Right. So now let's discuss solutions of the EL equations.
Sorry, S squared minus S squared squared.
Sorry, S squared, yeah, it's not there. Thank you. Oh, that's very important. So let's discuss solutions of the EL equations. So normally we think that we can choose some time slice, so we fix x naught, and then on this time slice we give sufficiently nice phi and d naught phi. And after that we have a Cauchy problem which hopefully has solutions. So we hope that Sol L is isomorphic to phi sigma, and this is phi of x d naught phi of x in R. So that's a huge vector space. But now what we can think, or like kind of, we can come up with a new definition which is physically motivated. We can say, what if we are interested in solutions of the Euler-Lagrange equation for which this charge E is finite? Of course, like finite energy, well, from the ecological point of view, that's probably a good idea, right? You don't want to create these solutions with infinite energy because then you kind of have to burn too much oil or whatever. So here inside, is sitting a subset, solely L finite, and these are solutions solely L for which the energy is smaller than infinity. Now, this was a vector space, so it didn't have any interest in topology. But now it's just a subset in this vector space. Who knows how it looks like? In particular, I won't be proving it, but let me make the following claim. Suppose that phi is an element of solely L finite. So then phi plus minus, which is a limit of phi x naught x1, x1 going to plus or minus infinity, is well defined for any x naught, and is equal to plus or minus a. So Of course, this implies that it cannot possibly change with time. So in fact, there are four possible scenarios. So you can start at plus a, and you can go, so this is phi of x1. So you can start at plus a, go to plus a. You can start at minus a, go to minus a, and you can start at minus a and go to plus a. So these are four possibilities. So all finite energy solutions, they have to belong to one of these four classes. So actually, Sol EL finite is a disjoint union of Sol EL finite alpha beta, where alpha and beta are plus or minus 1, and I label them, so this is a plus plus sector, this is a minus minus, this is minus plus and plus minus. So these are the pictures. So I think this claim, it's a little bit of analysis. I think in one of the problems, so the next problem set, maybe you don't have everything, but at least, well, they ask you to do a little bit of proofs in this direction. So perhaps a little bit about the terminology. The solutions of this type or of that type, they're called solitons. So solutions which where there is a change from one asymptotics to the other one. And perhaps you heard this story, the first solitonic solutions, these were waves observed in Britain on some canal, so some kind of special wave which was propagating along the canal, and then there was a kind of theory of solitons that's also a bit similar to the Wess-Zumino model. Probably there are like tens of thousands. Like this is an entry point to some literature of tens of thousands of, or thousands for sure, of items, like a huge theory of people studying interesting topologically non-trivial solutions of PDEs that emerge from the action functionals. In fact, in this model, you can compute some of them, and that we also ask you to do. So solutions of the EL equations, the specific form. I don't know whether you still remember from your course of PDEs, Riccati equations. So if not, you would need to rehearse it a little bit. So perhaps I would like to end with one more example of the same type. Right. So here we looked at the scalar field with some funny potential. And what about a complex scalar field? C. So I replace a real scalar field by a complex scalar field. So here I should replace brackets by absolute values. And V of phi, again, will be lambda over 4. Now, phi square minus a square squared. So again, if I'm not mistaken, EL equations will be of the form square phi plus lambda phi square minus a square. And the energy over R, and here 1/2 dx1. Of course, again, we can be interested in the finite energy solutions, right? So we can try to make a drawing. So that's the vector space Sol EL, the vector space of all solutions. And here inside is sitting Sol EL finite, so solutions with finite energy. Now we can also ask for solutions with lowest energy. What's the lowest energy? So here that's a sum of squares. So if you want so the lowest energy, we have to have E equals 0, right? And this tells us that phi is constant, and absolute value of phi is equal to A. So such solutions are constant solutions, and there is exactly a circle. So there is exactly a circle of those. So this is, so these are solutions with E equal to 0. Now, let me recall that in the theory of the free scalar field, we have a symmetry. Of rotation by a phase. So we looked at this symmetry before. Of course, one would need to check that this symmetry survives when we add the potential. But as you see already, right, the potential is invariant under this symmetry, so the chances are very, very good. So this symmetry, so the corresponding charge is integral over R, if I'm not mistaken, d naught phi bar minus d naught phi bar phi dx1, right? So that's the charge, the Noether charge which corresponds to this symmetry. And what this symmetry is doing, right? This symmetry is acting on Sol EL. It's easy to see that this action restricts to Sol EL finite, and it also restricts to the lowest degree. So we have this symmetry, the rotations, they act. So S1 Right? So our group is simply S1. So the circle corresponding to these rotations, it acts on the whole picture. In particular, it acts here. So remark. So S1 action on the E equals 0 subset is free. Indeed, what happens here, right? You just shift psi by theta, so you rotate this circle. And in physics, this is called the spontaneous symmetry breaking. So well, why so complicated words for such a simple fact? So if we had a fixed point of our symmetry, then we could have chosen the lowest energy solution, which would also be symmetric under the action of this symmetry. So the reasoning, I think how physicists imagine it, if equations have a symmetry, then solutions perhaps also should have a symmetry. But this is not necessarily the case. So we have this E equals 0 solution. We act by symmetry. The action is free. So there are absolutely no fixed points. You always move from one solution to the other. In quantum theory, there would be some consequences of this simple fact. But for us, in classical theory, simply what we observe, yes, this symmetry acts, and it turns out that here it does act freely. So there are some fixed points elsewhere, but not on the E equals 0, not on the E equals 0 surface. So sorry today, to be honest, we didn't prove much, right? So I more like introduced various constructions and gave you examples, but hopefully from time to time it's also okay. And then next week, after all, it will be gauge theory. So that's it for today.